So this video has to do with what's going on with the molecules. Why does volume and pressure, why do pressure and volume have that inverse relationship? You know, why, when you heat a sample, does the pressure go up if the volume is constant? You know, the various things that we learned about using the ideal gas law, it'd be nice to know, you know, why those things are true. And the reason why has to do with what the molecules are doing. And so that's what I'm going to be talking about in this video. So I start out talking about the postulates of the kinetic theory, and then I start talking about a distribution curve, because in a gas sample we have gas molecules that are not all moving with the same speed, and the way scientists handle things like that are with something we call a distribution curve, a curve that talks about the distribution of speeds within a sample. And at the very end, I'll mention the diffusion and effusion that I'll talk about more in class on Thursday, and that you'll deal with in lab on Thursday night. So if you want to be prepared, if you want to know what you're doing, you should watch the video. Okay, thanks.
Okay, so what is happening with the molecules, and how can we use this to help us understand the gas laws? All right, so what this starts with is a theory. It's called the kinetic molecular theory of gases, and it consists of a set of postulates or statements, okay? These are 5 postulates about gas molecules that may be used to interpret and understand the behavior of a gas sample. So I'd like to just go over what these postulates are and just say a few words while I'm talking about the actual postulates, and then use them to explain some things that we already know about the behavior of gases. Okay, so the first postulate seems pretty obvious. A gas consists of molecules in continuous random motion. In other words, gas molecules are always moving. They are not ever still. Okay, so they're always moving. All right. The second one is that they are negligibly small compared to the distance between them. They are very, very tiny indeed. They are like tiny specks. Okay. And the third one, I've sort of already talked about a little bit, and that is that the pressure exerted by a gas is due to collisions between gas molecules and the walls of the container. That is what causes pressure. Collisions. So collisions with the walls cause pressure. Okay? Gas molecules do not interact, meaning they don't attract or repel each other, so their their collisions are considered elastic, which in physics that means that they don't involve any loss of energy. They're like billiard balls. They just bounce off of each other without losing any energy. And the fifth postulate, which is a very important postulate, so I would say this is the most important, has to do with the average kinetic energy of gas molecules. And it says that the average kinetic energy, so that's the motion energy of gas molecules, is proportional to the temperature in Kelvin. Okay? And we'll be getting back to this later on. All right. So how do these help us understand gases? All right, so we want to understand gases. So how does this help to understand gases? All right, let's consider postulate number 2. Gas molecules are negligibly small compared to the distances between them. And if you think back to the very first class on gases this semester, which was the very first class of the semester, I talked about how gases are compressible. Okay, now we know why they are compressible. At least this theory helps us understand why. And the reason is that there is lots of empty space between gas molecules. So this postulate, like I should say postulate 2, explains why gases are compressible. Because they have so much empty space between them. Okay, so they can take up that space pretty easily when you push down on them. All right, so that was postulate number 2. Now let's think about pressure, okay? So let's try to understand, why does the pressure go up when the volume goes down? Okay, why does pressure go up when the volume goes down? All right, so let's look at postulate 3. The pressure exerted by a gas is due to collisions between gas molecules and the walls of the container. Okay, so if I have my syringe, like I showed you, my blocked syringe, okay, it's all blocked, it's not going anywhere, okay, and it's, I'm going to push on it, right? So I've got a bunch of molecules in here. "23 to be exact, maybe 25, there we go. And I compress, so I push down, try to draw a similar looking thing here. And I push down on this piston, or this plunger, whatever you want to call it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19. So you'd see how much more crowded they are. Okay, so I have a smaller volume. Okay, well, pressure is due to collisions. In fact, it is the force per unit area, and this force is due to collisions. That's what this postulate 3, tells us. All right, so when you have more molecules here in a smaller volume, what also is smaller, by the way, here you had all this area for those molecules to collide with. Here you have the same number of molecules, but look what's happened to the area. It's gone way down. So the area, this has gone down. So if the area goes down, that's going to make the pressure go up, because you have a greater force per unit area. So you have a greater force per unit area. So because we know that pressure is due to collisions with the walls, which it says in postulate 3, we can explain why the volume, when the volume goes down, the pressure goes up. Okay, so that's because you have smaller walls, you have a greater number of collisions per unit area. Okay, so postulate 3, which is all about how pressure is due to collisions, explains Boyle's law, because that's Boyle's law, that pressure goes down, that when the volume goes down, the pressure goes up, and the pressure is proportional to 1 over the volume, this inverse relationship. Okay, so we're on a roll here. Okay, so let's think about another thing. What happens to pressure as temperature goes up? Now, this is not particularly one of the gas laws, but it comes out of the ideal gas law, because P is nRT over V. So suppose we have a fixed volume. All right, we don't let the volume change. We have a box like this, all right? We have a gas inside the box. And we're going to heat the gas. So we're keeping the volume constant, and we are going to increase the temperature, okay? Now, you can see from the ideal gas law that if these guys are constants, that as temperature goes up, the pressure will go up. That pressure will be proportional to temperature if volume is constant, and moles are constant, of course. So you could see it from the ideal gas law, but if you think about what's happening with the molecules, as you heat this gas, what do the postulates tell you? So what happens as you increase the temperature of a gas? So here, postulate 5. The average kinetic energy of gas molecules is proportional to the Kelvin temperature. So as the gas is heated, its average kinetic energy goes up. Now, what is kinetic energy? Okay, kinetic energy is for one molecule would be 1/2 times the mass times the velocity squared. So what that tells you is as the temperature goes up, so as a gas is heated, it really means the temperature goes up. The kinetic energy goes up. That means the speed is going to go up, at least on average. We'll talk about average speeds later. So you can imagine you have all these molecules in here, and as you heat it, so as it's heated, they move faster. They move faster. They hit the walls with a greater, they hit the walls more often. So at a higher temperature, the gas molecules hit the walls more often and with a greater force. So we know that pressure is force per unit area, okay? And the force, the total force would be, you could think about this as being the force for a single collision, the force per collision, times the number of collisions, okay, per unit area. And at the higher temperature, you have a greater speed. So your force per collision goes up, and the number of collisions goes up. I may have already said that, but basically both of these factors lead to an increase in the pressure. That's pretty good, you know. I could just look at those postulates and explain quite a bit of our understanding of gases. All right. So I'd like to focus on this 5th postulate. I just want to focus on this because it is so important. Okay, so let's talk about it a little bit more detail. So it says that molecules move more quickly. That means they have greater speeds as the temperature goes up. And another part of it is that it mentions something. It mentions average kinetic energy, which is basically the average of 1/2 mv squared, averaged over all the giant number, Avogadros or more number of molecules in the sample. So it talks about averaging. Now, if you see a word average, all right, so you see this word average. So why do they have to use that word? Why is average even mentioned? What does that imply? You know, if all the molecules were moving with the same speed, then the postulate wouldn't have to say the average speed. Okay, so the fact that it mentions an average speed, the fact that it even brings that up, implies that gas molecules in the sample do not all move with the same speed. And that is a major conclusion here, that so all gas molecules in a sample are not moving with the same speed. There is an entire range of speeds. Okay, for molecules in a sample. So even if it's a sample of all carbon dioxide molecules at, 300 Kelvin or 500 Kelvin, even if they're all the same gas, there is always a range of speeds. Okay? They're never all moving with the same speed. So I would like to sort of bring up, how do scientists in general handle properties that can vary within a sample? And we deal with it in a very, very specific way. How do scientists handle properties that can vary within a sample? Okay, so let's talk about something that maybe is a little more familiar to us than molecules moving in a sample. Let's talk about heights of the people in the US population, okay? Okay, so what scientists would do to talk about heights of people in the country, where they would draw a graph, and this graph is called a distribution function. Okay, a height distribution function, which is what I'm going to sort of sketch for you in a second. A height distribution function is a graph where the y-axis is the probability of someone having a certain height as a function of height. Okay. So generally they would look kind of like this. This is a curve that has a name that a lot of you probably know. We would call this the probability as a function of height. This is called a bell curve. And so let me just talk about what it means, right? This is h that's varying this way. So what it means is that most people, you could see you have a high. This is the maximum of the curve right here. It goes up to a maximum. So this is where the curve is the tallest. Okay, so that means that you have rather high probabilities, large values of P of H, right in the middle. Okay, that most people have a kind of a regular height, right? So height is varying this way. This is where the very tall people would be, and this is where the very short people would be. Okay, but you actually have most of the probability is at medium heights. So let me just go. So this would be a very low probability of being this tall, rather short. And the probabilities get bigger and bigger as you get closer to the middle of this curve. So this is, the most probable height. It's also, because this curve is symmetrical, it's the average height. And, most people have an average height. And over here, as you go in this direction on the curve, here now you have your basketball players over here. So there's a very small probability, right, that you'll be very, very tall. Okay? All right. So the basic conclusions from this curve are that the probability is greatest for medium heights. Okay, so there are lots of people with medium heights. There's very few extremely tall or extremely short people. I'm talking about, these are very low probabilities. These are P. Here's the probability of being this small height. So the probability of being this tall is also very, very small. And I would like to point out the area under this curve, right? This is something a little more subtle. If I want to talk about the area under this curve, well, when you find an area under the curve, so it's as if, here's my curve, I got this big thing, and I've got my probability of being a certain height as a function of height. And if I take and I add up all these probabilities, so I take and I just go for every single probability, I add it all up. What is the sum of all those probabilities? You know, you have to be a height. Everyone has a height. So if you add up the probabilities of all different heights, all the different heights, it ends up being 1. So the area under the curve is equal to 1 because the sum of all the probabilities has to be 1. So that's a curious thing about this curve as well. Okay, so that's what's going on with a height distribution curve. How about a speed distribution curve? Does it look exactly the same? Well, not exactly. Similar, but not quite the same. So a speed distribution curve for molecules in a gas sample, right? That's what this is for. For molecules in a gas sample. Speed distribution curve is a graph of the probability of a molecule having a certain speed. So the probability of having a certain speed versus that speed. So this is speed here on the x-axis. And so is it a symmetrical curve like the height distribution curve? And the answer is no, not exactly. It's kind of a skewed. So it rises faster and then it decays more slowly. So it rises faster and decays slower. So it's a little bit, it's not as symmetrical looking as the other distribution curve. But most molecules here, as well as in the bell curve, most molecules have rather medium speeds, right? So the probabilities are sort of highest for rather medium speeds. So most molecules have medium speeds that they travel with. And we don't really care so much about the exact function. But what we see here is that there are few molecules that move very slowly, and that there are few that move very fast. Okay, the exact function doesn't matter to us really. It's just the overall shape. And another thing we're going to look at is how does the shape of this curve, oh, and by the way, this is called the Maxwell Boltzmann speed distribution curve. So how does the Maxwell-Boltzmann distribution curve for molecular speeds, how does it change as the temperature changes? Because we know temperature affects average kinetic energy, so therefore it affects speed. And how does it change as the molar mass changes? So that's the molar mass. In other words, how do gases that have greater molar masses, what happens to their speeds relative to, say, a sample that had very small molar masses? So let me draw the speed distribution curve for 2 different temperatures on this graph. Okay, so here's my P of V versus V. This is speed on the x-axis. This is the probability of a certain speed. I'm kind of a perfectionist, but oh, that's good enough. Okay, so here is a lower speed, and here is a higher speed. Okay, so this is, sorry, a higher temperature. Higher temperature and a lower temperature. Okay, so let's look and try to compare these 2 curves. So let's pick up a very low speed. So here's a low speed over here. This is a very slow speed. So what can you see is different about the two temperatures? So here is the probability for the higher temperature curve, okay? And here is the probability for the lower temperature curve. So you could see right away that the lower temperature has a greater probability of there being a very slow speed, okay? And the higher temperature has a lower probability of moving at a slow speed. That's probably a better way to say it. The lower temperature has a greater probability of molecules moving at a slow speed, and the higher temperature has a lower probability of molecules moving at a slow speed. So what does that tell you? That tells you that molecules are moving more slowly at the lower temperature. There are greater probabilities of moving at slow speeds, whereas for the higher temperature has a low probability of molecules moving at such a low speed, a slow speed. So now let's go to a higher speed, okay? So let me just continue this curve down a little bit here. So here's a pretty high speed here. Let's take this speed over here. So this very small probability so there is at high speeds there's a very small probability that the lower temperature gas will have molecules moving with a large speed. But if you look at the probability for the higher temperature, right now we're talking about a higher probability. This is a higher probability at a large speed. So there's a larger probability that the gas at the higher temperature will move at a high speed. So, this is a mouthful, looking at these probabilities. But the bottom line is, the higher the temperature, the greater the speeds will be. If you look at both of these curves and you say, well, where are most of the molecules moving? At what speed? So at this temperature, most of the molecules are moving at speeds like around here, okay? But at a higher temperature, most of the molecules are moving at speeds that are more like around here, okay? So this is most molecules, and this is a higher speed. And this is most molecules at the lower temperature. Okay. And another thing you notice with these curves, and that is if you look at the width. So if you sort of see how wide these curves are when it's like at half the maximum, you could see that you have a much wider curve. So this is another observation, that at higher temperatures, there is a much greater range of speeds in the sample. Okay, so if you're looking at a slow speed, if you're looking at a low temperature, you don't have that wide a range. But if at a higher temperature, you have actually a very wide range. So as the temperature goes down, this curve narrows. As the temperature goes up, it spreads out. And an interesting phenomenon that goes along with that is because these areas, the area under each one of these curves has to be 1, you get this flattening, you get this decrease in heights as the temperature increases. So as the temperature goes up, the curves get shorter because the range gets wider. And all the areas must equal 1, because at any temperature you have to have 100% or a probability of 1 that the gas molecules are moving at some speed. Okay, so those are the main conclusions here. Number 1, that molecules tend to move faster. At higher temperatures. Number 2, that the range of speeds increases as the temperature goes up. And number 3, that the curves flatten as the temperature goes up. And that's because the areas all have to equal 1. Okay, so that's what happens as the temperature changes. So I said we were also going to look at what happens as molar mass changes. And actually, you sort of see a similar behavior as the molar mass decreases to what happens as the temperature increases. Okay, so just to draw that for you, here's the probability of a certain speed versus speed, and this is for a very large molar mass, and this would be for a much smaller molar mass. Okay, so you could see that most of the molecules here move relatively more slowly. I'll go relatively slower, that's what I'll say. And here, most molecules move relatively faster. Just write faster. Okay, well that's because the heavier molecules are moving more slowly and the lighter ones are moving faster. So that's a big conclusion here. Heavier gas molecules move on average more slowly than lighter ones. Okay. Also, you could see that as molar mass increases, the range, this range, goes up. Okay, so here you have a smaller range. You have a smaller range of speeds with a larger molar mass. And here you have a larger range of speeds when you have a smaller molar mass. So that's very similar to what happens as the temperature goes up as well. There's another thing I want to tell you, and that is, I've been talking about how in the larger molar mass you have most molecules that move more slowly, and here you have most molecules moving more quickly. So turns out that the average speed, or one of the measures of the average speed, we actually call it the root mean square speed. But you know what? It's okay if you think about it as the average speed. It's a little different from a real average, but it's really not important to us here. So the root mean square speed, which you can think of as an average speed, we call it the RMS speed, is equal to the square root of 3 RT divided by the molar mass. Okay, this is really cool because it really allows us to calculate what the root mean square speed would be. Maybe I'll do one of those calculations for you. I just got to get rid of this. Okay. So let's suppose I wanted to figure out what is the average speed of an ammonia gas, of course this is all gases, molecule in a sample at, let's make it near room temperature, 300 Kelvin. Room temperature is 298. Okay, so I'm going to show you how to do this. But there's a little bit of a tricky part to this, and that is that the R has to be in a different unit than we're used to. So R, we have to actually use 8.314 joules per mole Kelvin. So we know 0.08206 liter atmospheres per mole Kelvin, but that will not work here because we're not dealing with liters and atmospheres here. We'd never be able to cancel those units. Turns out liter atmospheres is a very odd energy unit, but joule is a much more common energy unit. So we don't use this here, not for this type of problem. So when you're figuring out an average speed, what you need to do, first of all, we're talking about ammonia. A nitrogen is 14, hydrogen is 3, so that's 17 grams per mole. It turns out that there are kilogram units as part of the joule unit. So when you're doing a problem like this, you must convert this to kilograms per mole. So it would be 0.017 kilograms per mole. So once you do that, you convert your molar mass into kilograms per mole. Then this is not too difficult a calculation because the root mean square speed is just the square root of 8.314 joules per mole Kelvin, 300 Kelvin over the square root, oh sorry, the square is already there, over 0.0170 kilograms. Okay, so I'm gonna get a calculator and do this. So what do you think this number is going to come out to? 10? 10, it's going to be in meters per second. 50? 100? Okay, so this comes, I have to take the square root of 440153, and it is literally 663 meters per second. So that's the other thing, is that a joule is a kilogram meter per second squared. Is that right? Yeah. Okay. So that's why you're going to end up with meters in your answer here. Let's see if this works out. 1 kilogram meter per second squared is a joule times Kelvin. Where is it? That's a joule. Joules per mole Kelvin times Kelvin, because of the 300, times kilograms. So kilograms cancels, Kelvins cancels. Oh, it's kilogram meter squared per second squared. Sorry, made a mistake. So we end up with meters squared over second squared, and when you take the square root of that, you get meters per second. Then I don't know what happened to the mole there. I don't think it really matters though. Yeah, this is kilograms per mole, so I forgot that. There, now it works. All right, you don't have to worry about the units, but basically you need to know that you get the answer in meters per second. So, okay, anyway, here's the thing. This is huge. Look at that speed that these gas molecules on average are zipping around with. It's just enormous. I love that. I think it's very surprising. But the main deal here, though, which I should have pointed out again, the main thing, get rid of this, is that as the molar mass increases, so as this gets bigger, that denominator is going to get bigger, and the root mean square speed decreases. And that's kind of what we saw on those graphs. We saw that as the molar mass increased, the average speeds got slower, and that's sort of borne out by this equation. Now, I didn't derive this or tell you where this came from, but if you're interested in that, you can take PChem in your senior year, or if you're a chemistry major. And we'll talk more about that there. So these are just some nice drawings that I got from a book. Actually, they got them from Pearson. And it shows how, what I just drew, that as the temperature goes up, the average speeds increase, right? This has the average, more molecules moving with this high speed, and here this has more molecules moving with a much slower speed. And you can see how these curves spread out. The range increases as the temperature goes up. Okay, so that's just a nicer picture. And here you could see actually some labeled curves for different gases. And you could see of the gases here, oxygen is 32 grams per mole, nitrogen is 28, water is 18, helium is 2, and 4, and hydrogen is 2. So you could see that as the molar mass decreases, the speeds go up and up and up. This is all grams per mole. Okay. And what else? Right? And that's all. That's all. In class, I'm going to talk about diffusion and effusion. And diffusion, maybe if you have a room and you open up a bottle of something really smelly in one corner of the room, let's say ammonia, that these vapors will eventually move all over the room. And it turns out that the rate of diffusion of a gas, is actually proportional to the root mean square speed. Okay, so that means if you have lighter molecules, they will diffuse faster. If you have hotter molecules, they will also diffuse faster. Effusion is similar to diffusion, but it has to do with molecules moving through a small opening from a region of higher pressure to a region of lower pressure. And the effusion rate is also proportional to the root mean square speed. And in lab, we're actually going to, so that would mean the root mean square speed is proportional to the square root of the molar mass, but we're actually going to look at the time of effusion. So when something has a fast rate, it happens in a short time. So time and rate are inversely proportional. So time, oh, sorry, did I get that wrong? Well, this is 1 over the molar mass. Yeah, the effusion rate is proportional to the root mean square speed, but as the mass increases, the speed actually goes down. So I had that wrong. It's the time of effusion that's actually proportional to the square root of molar mass. And this is going to be used in lab on Thursday night. But I'm going to talk about it in class before then. So that's all I have to say.